Good evening, everyone. My name is Nidhi. In this video, I'll be walking you through the entire process of implementing a machine learning model to predict autism spectrum disorder. We have implemented three different models, such as XGBoost classifier, random forest, and decision tree as a team. But I alone have worked on XGBoost classifier. So we'll just discuss the data pre-processing and feature engineering, what are the model implementation along with the performance metrics, and also with the because mine is the best performing model compared to the three, we will also be discussing about the error analysis, latency, and scalability. And but for now, I'll just be focusing more on the XGBoost classifier model. The first task was to merge these data sets, ensuring that only the common column across all the data sets were kept. This step was critical because missing or inconsistent data could have led to incorrect predictions. So I'll just execute this cell. In this cell, we are just reading all the just the raw files, and this is the step where we clean all the data. So we are working on merging the data. After merging, we clean the data by removing unwanted columns like case number, ethnicity, and country, which do not contribute to predicting on AST. We also removed high cardinality columns and handle missing values using the techniques like drop now. Columns like sex and jaundice were encoded using label encoding to convert them to binary format, making them suitable for machine learning models. So I'll just execute all the codes one by one. So this is a step where we clean all the data. As we can see, we change the column names and drop some unwanted columns also. And we just also here categorize the data from 0 to 1 for jaundice. If this jaundice is yes has 1 and no for 0. And after that, we used to work on the exploratory data analysis to understand the clean data. So I'll just execute this code. This will help us to, based on these graphs, one of the major issues with this data set was that there's a class imbalance with around 65% was non-AST and only 35% were called as AST. So address this, we had to use smooth, that is synthetic minority oversampling technique. Smooth works by generating synthetic instances of the minority class. In our case, that is the autism class, which helps to balance the data set and allow the model to learn from both classes more efficiently. This process was crucial to ensure that XGBoost model not o- model did not bias its predictions towards the majority class and could perform well on predicting AST cases. And they were also able to see the distribution of A scores from A1 to A10. So all were distributed across 0 and 1. And few other features like A3, A6, A9 were not because they were not common across all the data sets. And we also implemented the feature correlation matrix. This shows that the data are unique, which will be helpful to that for the model's performance and development. And now let's directly go forward to the XGBoost model implementation. So we chose XGBoost due to its performance with structured dataset and its ability to handle imbalanced data well. Here's the implementation of XGBoost model. We just first set up the hyperparameters such as max depth is equal to 6 to prevent overfitting by limiting the depth of the decision trees. Learning rate is equal to 0.10 for gradual learning. Subsample is equal to zero point 0.8 and call sample by 3 is equal to zero point 0.8 to add randomness to each tree and avoid overfitting. N estimators 300 to train 300 trees. We also use eval metric is equal to AUC to evaluate the model based on AUC, which is particularly useful when dealing with imbalanced data sets. Smooth was applied to balance the training data before training the XGBoost model. After training the model, we predicted probabilities for this data, applied a custom threshold of 0.42, and evaluated the performances. So I'll just execute this code now. As we can see, the model achieved an accuracy of 90.58%, which is a good indicator that the model is correctly classifying instances. The precision was around 85%, meaning that when the model predicted a case as autism, it was correct 85% of the time. Recall was around 87%, which tells us the model correctly identified 87% of all true autism cases. This is an important metric because we want to minimize false negatives in medical applications. F1 score was identified as around 86%, that is the harmonic mean of precision and recall, providing a balanced evaluation of model's performance. And the ROC AUC was around 96%, which is excellent and confirms the model's ability to distinguish between ASD and non-ASD classes. We also plotted the XGBoost feature importance, that is, which are the columns that are helpful in identifying the ASD classes. So I'll just run this. So as we can see, they feature A5, A4, and A7 with the three classes that were responsible for the correct prediction of classes. We also plotted the ROC curve to visually assess the model's performance. The ROC AUC score for XGBoost was highest among all the models at 0.9652, which indicates its superior ability to differentiate between autism and non-autism cases. As we can see in the graph, I'll, I'll just execute the score. As we can see in the graph, the curve is closer to the top left corner, signifying the high model performance. Talk about the latency and throughput calculation for all the three models. I'll execute this code. As we can see, the XGBoost model has a latency of 5 seconds and a of around 100,000 and change. While XGBoot has slightly higher latency and compared to simpler models like Decision Tree, its higher AUC and overall performance justify its use. We also evaluated scalability. XGBoost performed well as even the dataset size increased. The training time did increase with the data size, but it scaled efficiently and didn't experience any performance bottlenecks. I'll just execute this. And we also that the training time also increases when data size increases, and the AUC score also increases with when the training size data set is being increasing. And we also perform the error analysis, and we found out that the model struggled for false positives, predicting autism when the cases were non-autism. The features A1, A5, and A8 had high values. For false negative, missing true ASD cases, the features A2 and A4 had lower values. This analysis helped identify patterns in the data where models is making mistakes and can guide us in improving the model or adjusting the feature selection process. Last but not the least, let us walk through the confusion matrix. This XGBoost model, out of 536 actual ASD cases, 460 were correctly predicted and 76 were false negatives, meaning they were missed by the model. For the non-ASD class, 940 instances were correctly predicted and 74 were false positives. This matrix highlights that while the model is effective, there are few instances where it might miss positive cases or incorrectly label negative cases as positive. In conclusion, XGBoost performs excellently across various metrics, outperforming both random forest and decision tree models. It showed great accuracy, recall, precision, and AUC, while handling class imbalance effectively with SMART. This model is highly reliable for identifying ASD cases, making it a strong candidate for real-time deployment in healthcare settings. For future work, we could experiment with more advanced sampling techniques, include other features like audio or visual data, or even implement deep learning models for better results. Thank you.